This is a spectrum from the NIST database for the compound ethyl benzene. How would I go about interpreting some of the peaks on this spectrum? Well, typically the first peak you focus on is the molecular ion, the one with the highest mass to charge ratio, because that tells you the mass of the ion. So in this case, for example, there is a cluster of peaks here centered around 106, which is the highest mass to charge ratio, which corresponds to the molecular mass of the compound. How would I check that? Well, you can use the average weights that you can find in a periodic table, the atomic masses you can find in a periodic table for carbon and hydrogen. The problem with using that is that those are weighted averages. They reflect the isotopic composition of those atoms in the environment. They reflect that when you have a sample of carbon atoms, most of your carbons will be carbon-12 atoms, but there will be 1.3% of those atoms that will be carbon-13. So it's much better to use isotopic masses for the most abundant isotopes for the elements of the structure you have. And a good way to do that without having to go with to troll through a list of isotope weights, or you can find them online, is to use an online calculator. This is the one I suggested in the Blackboard that you can use, and you can type here the formula you're interested in. In this case, is C8H10. And you can get a low resolution spectrum, or you can have a high resolution spectrum, and that will give you more or less a fewer peaks in that cluster of peaks. You can also play with the abundance, or having it at a very low sensitivity, so it only picks on the most abundant isotopes, or with a very high sensitivity in which it picks with very unlikely isotopes and isotopic combinations of the different atoms in the structure. So if I select high resolution but not a particularly high minimum abundance for my C8H10, and I click calculate plot, it tells me that I should expect a peak, the main peak, to be at 106 mass to charge ratio. And if I go to my spectrum, I can see that yes, as I was expecting, the most abundant peak in that particular cluster that corresponds to C8H10 with the one at 106. So this fragmentation peak is actually the molecular ion of the molecule. It corresponds to the full structure of the molecule. And look at how I'm writing it in square brackets and with a plus. And that's because it's an ion. I've knocked off. It's a positive ion. I've knocked off an electron. The spectrometer has knocked off an electron. And I would say the fragment C8H10 in brackets and with a plus has a mass to charge ratio of 106. The next more interesting peak, which in this case happens to be the base peak, the one that is at 100%, is the peak at 91. And if I calculate the difference between 106 and 91, that's a difference of 15. And if you think of the table of common losses that I suggested in the slides with the content for this week, it suggested that a loss of 15 typically indicates the loss of a methyl group, which would not be unlikely if you think that you could lose this 5-terminal carbon. So then if you lost a methyl group, that means that you're losing 1 carbon and 3 hydrogens. So your structure, the potential structure for that peak would be C7H7. So if I go to my isotope distribution calculator and plot and type C7H7 and calculate what would be the most abundant peak, and look at the plot, it specifically tells me, yes, at 91 mass to charge ratio, you would have a peak of 91 and would be more abundant in that cluster. You can see many decimal places. That's because I've set it up to high resolution. If you put it at low resolution, it will give you the mass with a much lower accuracy, and it will reflect better what we have in the spectrum. So you can choose the level of accuracy depending on the level of resolution, depending on the resolution of the spectrum you are working with. So I would go to my master spectrum and I would be able to identify this fragment as the fragment C7H7 with a mass to charge ratio of 91. In this case, it's likely that the structure of that fragment is this one, the benzene ring with a CH2. However, sometimes there are changes that happen inside the mass spectrometer, and it's related to the fact that you have high energy ions and they are being accelerated. So it's sometimes a bit tricky, it can be a bit risky to suggest the structure of the ion, the structure of the fragment, because there might be changes, chemical changes that happen inside the spectrometer that we have no control over. So my suggestion would be that you do not suggest the structure of the ion unless you have been asked to, but simply to what mass it corresponds, in a similar way I've done here. And another peak that I might be interested in identifying is the ones here in this sort of 77, in the 77 mark. And those are likely to correspond to the benzene ring, so having lost the whole of the ethyl group. So if I go to the molecular distribution calculator, isotopic distribution calculator, it will tell me, you know, what would be the most abundant of those peaks, and I will be able to hopefully, confirm my idea that that's likely to be the benzene ring ion, the ion corresponding to the benzene ring. So the benzene ring would be C6 because it has 6 carbons and 5 hydrogens, since the 6th hydrogen is actually there is no hydrogen, it's a methyl group in that carbon, that substituent. So if I type that in our calculator, isotope calculator, it suggests that the most abundant of the series of peaks, although they're quite mixed in our spectrum, would be a peak at 70 mass charge ratio of 77. So if I go back to my spectrum, I would be able to identify this peak as a C6H5. Again, with square brackets and with a positive charge, because that's how you write fragments, ionic fragments for mass spectrometry. So remember, do not use the atomic weights or atomic masses in a periodic table, because those are weighted averages of the different isotopes. Use either a list of isotopes and choose the most abundant isotope for that element, or the isotope calculator that I've suggested, or another one you might find online. Always calculate losses from the molecular ion. So compare all the peaks to the molecular ion. And I would suggest that, because you cannot assure what's going to happen in the spectrometer and how the bonds are going to break, but what you do know is that all the atoms that are formed, are all those fragments will come from the original molecule. So if you always go back to the fragment that represents the original molecule and calculate losses from there, you will be able to identify, hopefully, what fragments of the molecules have been lost. And finally, my suggestion would be that you do not focus on all the peaks, interpreting the whole spectra, but you pick a few of the most abundant peaks and see if you can identify them. And I would suggest that you do not focus in very low mass to charge ratios. Although, for example, I can just spot here a 15, which is probably indicative, that peak suggests that's attributable to a CH3. So I might as well just identify since I have just spotted it. But in general, I will suggest to stay in the highest, the largest peaks, the tallest peaks, and in higher mass to charge ratios, because you can find very, very small fragments in the lower part in the smaller section of the mass to charge ratio axis. So this is all from me. I hope it was useful to interpret to solve the exercises. And as usual, if you have any questions, drop me an email. Thank you for watching.